What if I told you that the biggest revolution in aviation today isn't in the shape of the wings or in the cockpit, but right here, in the blazing heart of the engine? The blades of an aircraft turbine operate in one of the most hellish environments ever created by man. They endure temperatures that would melt steel, brutal centrifugal forces, and a constant chemical attack from corrosive gases. For decades, improving engines meant improving the materials of these very components. In the last 5 years, we've witnessed a series of quiet but monumental breakthroughs that are rewriting the rules of the game. Today we're going to break down the 5 material advancements that are enabling engines to be more efficient, lighter, and more sustainable than ever before. Fasten your seatbelts. Let's start with the undisputed kings of the hot section, nickel superalloys. They've been the foundation for turbine blades for decades because of their incredible strength at high temperatures. But innovation hasn't stopped. The big leap has been the refinement of single crystal or SC alloys. Imagine that instead of being made of many small joined crystals, the entire blade is one giant crystal. This eliminates grain boundaries, which are weak points at extreme temperatures. We've gone through several generations. The 3rd and 4th generation alloys, for instance, incorporate elements like rhenium and platinum group metals to allow them to operate at even higher temperatures. And now, innovation is merging with manufacturing. Companies like EOS have developed new nickel superalloys like in 738, designed specifically for 3D printing. In fact, the company Precision ADM has already produced blades with this material that withstood tests at 110% of standard operating RPM and temperatures of up to 1,700 degrees Fahrenheit. Now let's move on to one of the most disruptive changes: ceramic matrix composites, or CMCs. Forget everything you think you know about ceramics being brittle. CMCs are lightweight, about 1/3 the density of metal alloys, and have far superior heat resistance. GE Aviation is the pioneer here. They are already using CMCs in the CFM LEAP and the massive GE9X engines. The result? Engines can run hotter using less cooling air, which translates directly to better fuel efficiency. To give you an idea, by 2021, the CMC components in LEAP engines had already surpassed 10 million flight hours. Of course, there are challenges. Manufacturing complex shapes is still difficult, and these materials require special coatings called environmental barrier coatings to protect against oxidation. But their adoption is unstoppable and represents a quantum leap toward lighter, more efficient engines. Let's leave the hot section and move to the front of the engine, to the massive fan blades. Here, the star material is advanced carbon fiber composite. Its incredible stiffness-to-weight ratio compared to traditional titanium allows engineers to design larger, thinner blades. Larger blades move more air, improving propulsive efficiency. The most spectacular example is the Rolls-Royce UltraFan engine. Its carbon composite blades measure a record-breaking 140 inches in diameter. That's nearly 12 feet. And to protect them from impact, they have a titanium leading edge. This engine promises a 25% improvement in fuel burn compared to the first generation of Trent engines. And it's not just Rolls-Royce. CFM International's RISE program also plans to use 3 dewoven carbon fiber blades. And GE Aviation has been using this technology since the GE90 back in 1995. It's a mature technology that continues to evolve to push the boundaries of efficiency. If nickel superalloys are the present and CMCs are the now, then niobium-based alloys are the next frontier. We're talking about materials for turbine blades that could potentially operate at 1,300 degrees Celsius or higher. To put that in perspective, the best nickel superalloys are reaching their physical limits at around 1,100 degrees Celsius. Companies like Questech Innovations, in collaboration with Pratt Whitney and NASA, are developing these niobium alloys for use with 3D printing, thanks to support from advanced research programs like the US government's ARPA-E. The main challenge is their resistance to oxidation, so the development of protective coatings is key. While this is a longer-term technology, niobium alloys promise a leap in thermal efficiency that could once again revolutionize engine design. Our final breakthrough isn't a material, but a way of making them: additive manufacturing, or 3D printing. Its impact cuts across everything we've discussed. 3D printing allows for the creation of geometries that are simply impossible with traditional casting or machining methods. Think of internal cooling channels with organic, super-efficient shapes, or lighter, stronger structures. GE already has more than 10 FAA-certified 3D printed parts flying in its commercial engines. Pratt & Whitney Honeywell All the major players are investing heavily in this technology. Additive manufacturing speeds up prototyping, reduces material waste, and, most importantly, unlocks a new level of performance by enabling optimized designs that previously only existed on a computer. Refined nickel superalloys, lightweight ceramics, giant carbon composites, futuristic niobium alloys, and a revolutionary way to manufacture it all. The trend is clear: the pursuit of lighter, stronger, and more heat-resistant materials. Every gram saved, every extra degree of temperature withstood, translates into less fuel burn, lower emissions, and ultimately, a more sustainable future for aviation. The collaboration between materials scientists and engine manufacturers is what is forging this future in labs and factories around the world. Which of these technologies do you think will have the biggest impact in the next decade? Let me know your thoughts in the comments. If you're passionate about aerospace engineering, don't forget to subscribe for more technical deep dives like this one. Thanks for watching. I'll see you in the next video.